Okay, so one of the last, I suppose, or one of the other little things to consider in terms of even just setting up kind of basics for integration is really diving into that idea of integration as the reverse of differentiation. So I suppose that's how we've introduced it in the first place, and that's kind of how we've defined integration from the get-go. But even just looking a bit more in depth at that, we don't have a rule for product or we don't have a rule for quotient, but some questions may require us to do these sort of calculations. And one way of doing that can be to work with the derivatives and to kind of relate derivatives of one function with maybe integrals of another function. And really what we're doing is we're setting up something which is an established rule for integration and kind of integrating by parts to some extent. But in terms of our course, we don't necessarily need to know the explicit kind of rules for that integration, but rather use that idea in computing given integrals. Okay, it's not that common of a question, but it has appeared and it is just something to kind of be aware of because it always has the potential. Um, so usually this would be used maybe for functions that aren't in the formula and tables book, or as I say, maybe products of a function or something along those lines. Really, products is probably the most common one we kind of see. And what we'll usually have to do is maybe differentiate a related function and then makes use of this relationship. The integral of a derivative gives me the original function. And we can usually use that then to manipulate the question in some way. So let's look at an example of this then. If I'm given this function, which we can see straight away is a product of two functions because x appears in two places in two distinct kind of functions. So x itself is a function and then sine 2x, x appears there also. So it is a product. We're asked to find the derivative. So to find the derivative, it's a product rule. So u is x, du dx is 1, v is sine 2x, dv dx is 2 cos 2x, and the overall derivative of the function then is u dv dx, so x times 2 cos 2x plus 1 times sine 2x. So 2x cos 2x plus sine 2x. Okay, and that's my derivative. So that's f dash x here. I'm told to use my result, so I know straight away, right, we're using that answer, to find the integral of 2x cos 2x. Now, straight away I can kind of see, right, in the example I've just done, that is one of the parts of the derivative here. And I know as well that integrating f dash x should get me back to f of x. That's the definition of an integral here. Okay, so making use of that, we are basically saying if I integrate 2x cos 2x plus sine 2x, that should get me back to x sine 2x. Okay, that's the idea that we're setting up here. If I integrate this derivative, okay, and I'm even going to put brackets around it just to show that we're using all of it. If I integrate all of this function, that should bring me back to the original function because I just differentiated to get this answer in the first place. And these are supposed to be inverse operations of each other. Now we know as well that an integral of a sum can be split out to be a sum of integrals. So dx on both of these. And again, keeping it still equal to sine 2x here. Okay. And again, I now have maybe isolated the part that was required in the question. So we'll keep that on its own here on the left hand side. So 2x dx is x sine 2x minus the integral of sine 2x dx. And all that's left for us to do is to compute any integrals we can. We cannot compute this integral on the left, nor do we have to, because it just asked me to find or to nearly express that or express the value of it. I can keep the x sine 2x as is, and I need to integrate sine 2x here, which is going to give me minus cos 2x over 2. I feel like that's one that we keep doing. So 2x cos 2x dx equals x sine 2x plus cos 2x over 2. Okay, and that's my overall answer. So without actually integrating a product, I've in fact used a different relationship to help me find the integral of this 2x cos 2x using the relationship that I had with the original function from the first part of the question there. Okay, so let's just look at one or two more examples of this. So the 2014 sample paper, I think, is the time that this has appeared really, and kind of the only time really that it's appeared. So find the derivative, first of all, of the function. So the function is x ln of x. Again, it's a product. So x is u, and then du dx is 1. V is ln of x. And the derivative of ln of x from our derivative rules is 1 over x. So my derivative here, dy dx, or indeed h dash x, I suppose, for this question, is u dv dx, so x times 1 over x plus v du dx, 1 times ln of x. So 1 plus ln of x is my derivative here. Hence find the integral of ln of x. Okay, so again, I'm looking at the question and seeing, right, I can see where that is in my derivative here. I'm making use of that idea that I know the integral of a derivative is the same as my original function. Okay, I have that relationship. So the integral of 1 plus ln of x dx is equal to ln of x. That's going to be, see, integral of 1 plus integral of ln of x dx equals ln of x. Okay, I'm getting happy now. So integral of 1 is just x. Integral of ln of x is fine because that was the question. And my overall answer then is that the integral of ln of x dx is equal to ln of x minus 1. Okay, and that's as far, or minus x, excuse me. That's as far as we can go. Okay, and we'll include a plus c as well. Given that it's not a definite integral here, including the plus c, I suppose, just absolutely ensures that we've accounted for any possible constant terms that could be there in that integral. Okay, we'll look at one more example of this again, and following the same idea here again. First of all, find the derivative. So again, u is x squared, du dx is 2x, so a bit more maybe to do with this one. V is ln of 3x, so let's look at the derivative of this one. So the derivative of this one, 1 over 3x, that's the derivative of ln. Then we need to consider the derivative of the 3x part, which of course is just 3. So we get our 1 over x, essentially as normal here for any ln there. Then dy dx, which of course in this question is f dash x as well, is u dv dx, so x squared times 1 over x plus v ln times 3x du dx 2x. So we get x plus 2x ln of 3x. Looking at part 2, I can already see again the part that I want there in the derivative of f. So I know I'm using that same connection again, that the derivative of x integrated should bring me back to that original function f. So let's look at doing that. Integrating x plus 2x ln 3x dx. And that should be equal to x squared ln of 3x. So that's the integral of x plus the integral of 2x ln of 3x equals x squared ln of 3x. Okay, and we're essentially following all the same steps here now. So we'll bring that integral of x to the right hand side. We can also integrate it as well to be x squared over 2. And we can include our plus c as well at the end there. Okay, so really for all of these questions, I suppose the key things you're looking for are an integral that you cannot compute because you don't have the rules or you're not familiar with the rules. So particularly products essentially is what we're seeing here. So any sort of product rule, we don't have a rule, or we don't learn the rule to be able to do. So we need to look at another way of doing it. And that other way is going to rely on another relationship with a pre-existing function. So I suppose for this sort of question, they nearly have to have kind of given you an earlier function to work with. And then it's about you identifying where that function is in the integral and making that connection between an integral of a derivative and the original function that it comes from. Okay, and just watching out there, as we say, therefore, those different products, and including that constant of integration there at the end as well. But yeah, but a slightly different type of question, but an interesting question nonetheless.